Berks County, Pennsylvania, July 1901. While his neighbors threw up quick plank potato houses in 8 to 10 days, Johann Keller was still hauling limestone in late June. They called it wasteful. They called him a fool. He dug 8 feet down and built walls 2 feet thick, a 12 by 16-foot barrel-vaulted stone chamber that took 6 weeks and 30 tons of local limestone. His neighbors finished their simple sheds for a few dollars in milled lumber. He spent 2 months on what they insisted was overkill. Then the heat wave hit. 96 degrees in the shade, day after day, for nearly 3 weeks straight. The worst summer heat Pennsylvania had seen in decades. Standard plank sheds climbed to 90 degrees inside. Neighbors watched helplessly as their potatoes sprouted and rotted, their stored vegetables turning to compost in the sweltering air. But that fool's stone vault? The thermometer nailed inside the door read 52 degrees, a 44-degree difference from the blazing air outside. While his neighbors lost 30 to 60% of their winter food stores, his vault kept 95 bushels of potatoes firm and cool, untouched by the killing heat. What did this Pennsylvania German farmer understand about the earth beneath his feet that everyone else missed? And how did his wasteful stone vault become the lifeline that saved 3 families from a hungry winter? If you value stories of practical wisdom that stood the test of time, make sure to subscribe. We've got more documented accounts worth remembering. Comment your city and time. We love reading where these documentaries reach. Johann Keller wiped limestone dust from his hands and surveyed the excavation that had consumed his mornings for the past 3 weeks. The hole measured 16 feet by 20 at the surface, tapering to 12 by 16 at the bottom, 9 feet down through Pennsylvania clay and shale that had fought him with every shovelful. His neighbors passing on the lane shook their heads at the sight. Elias Brandt had stopped by twice already, leaning on his fence post to offer unsolicited advice about the foolishness of digging past 4 feet when a simple above-ground shed would keep potatoes just fine through winter. The criticism stung because Johann knew it carried the weight of local consensus. Every farm within 5 miles stored root vegetables in quick plank structures, 10 by 12-foot potato houses with board walls and tar paper roofs that a man could throw up in 8 to 10 days for the cost of milled lumber and nails. These neighbors had been farming Pennsylvania soil for 2 generations, and their methods worked well enough to keep families fed. But Johann had grown up listening to his grandfather Friedrich's stories of the old country, where stone cellars dug deep into hillsides kept food cool through summers that could bake a man senseless and warm enough through winters that would freeze a wooden shed solid. The decision to build the vault had crystallized during the previous summer when Johann's own modest root cellar, a simple dugout with plank walls, had failed him during a week of 90-degree heat. He had opened the door to find his seed potatoes sprouting green shoots and his winter onions soft with rot. The loss had cost him 20 bushels of food and nearly $40 in wasted crop, enough to feed his family for 6 weeks. That night, counting his remaining stores by lamplight, he had resolved to build something that would work regardless of what the weather threw at him. The design came from Friedrich's memory of Palatinate farmsteads, where barrel-vaulted stone cellars had served families for centuries. Johann would excavate to 8 feet below grade, lay limestone walls 2 feet thick, and crown the structure with a curved stone arch that could bear the weight of 4 feet of compacted earth. The finished interior would measure 12 by 16 feet with 8 feet of clearance from floor to crown, large enough to store 100 bushels of root vegetables on wooden racks, with room for a man to walk between them. Construction began with the centering, a wooden framework that would support the archstones until the mortar cured. Johann spent 2 days shaping oak ribs into the precise curve he needed, spacing them 18 inches apart and decking them with inch-thick planks. The form had to be perfect, because once he began laying voussoirs, the wedge-shaped stones that would form the arch, any deviation would create weak spots that could bring down the entire roof under the weight of earth and winter snow. The limestone came from a quarry 3 miles east where Johann could select each stone for size and shape. He needed roughly 30 tons of material, flat stones for the walls, carefully shaped voussoir for the arch, and a single keystone that would lock the entire structure together. The hauling alone took 10 days with his draft horses, each load representing 12 to 1,500 pounds of stone that had to be lifted, loaded, transported, and stacked near the excavation. Laying the walls required skills Johann had absorbed through years of helping his grandfather repair spring houses and barn foundations. Each course had to be perfectly level, with stones selected for tight joints and minimal mortar gaps. The lime mortar itself demanded patience, mixed from quicklime, sand, and water, in proportions that Friedrich had taught him, then allowed to slake for days before use. Unlike the quick-setting Portland cement that some builders were beginning to favor, lime mortar cured slowly and remained workable for hours, giving Johann time to adjust each stone for the best fit. The arch represented the project's greatest technical challenge. Starting from both side walls simultaneously, Johann laid voussoir in careful progression toward the center, each stone cut to shed its load downward and outward into the supporting walls. The stonework work required absolute precision. A single poorly fitted stone could create stress concentrations that would crack under load. When he finally set the keystone in place, tapping it home with a wooden mallet until it locked tight against its neighbors, the arch became a single structural unit capable of supporting tremendous weight. Mr. Carter from the general store made a point of stopping by during the backfilling phase, when Johann was shoveling the first loads of earth over the completed arch. "You know, Johann, they make fine potato houses now with proper ventilation and good tight boards," Carter observed, gesturing toward a seed catalog illustration he had brought along. "Fellow could have 3 of them built for what you've spent on this hole in the ground." The merchant's tone carried the authority of a man who sold modern solutions to practical problems, backed by printed materials from agricultural suppliers who understood efficient farming methods. Johann nodded politely but continued his work. The earth cover would eventually measure 4 feet deep at the crown, planted to grass that would shed rain and provide additional insulation. Below this protective layer, his stone vault would sit surrounded by soil that maintained a nearly constant temperature of 50 degrees year-round, a fact his grandfather had taught him and that Johann had verified by driving a metal rod 8 feet into undisturbed ground and checking its temperature through the previous winter and summer. The finished structure cost Johann 6 weeks of hard labor, hired help for the heaviest lifting, and roughly $60 in materials and wages, triple what his neighbors spent on their frame storage buildings. But by late July, when he moved his first loads of new potatoes down the 7 stone steps into the vault, the interior temperature held steady at 51 degrees, while the summer air above baked at 85. The thick walls and earth cover had created exactly what Friedrich had promised, a space where the seasons touched lightly and food could wait in cool darkness, regardless of the weather's fury above. The heat began building in mid-July, with a series of cloudless days that pushed temperatures into the low 90s across southeastern Pennsylvania. By the 21st, Harrisburg's weather station recorded 97 degrees, and farmers throughout Berks County watched their corn leaves curl and their livestock seek shade by mid-morning. Johann checked his vault's interior temperature each evening, noting the steady 51 degrees on the mercury thermometer he had mounted inside the door. Outside, his barnyard thermometer climbed past 95 degrees 3 days running. Elias Brandt discovered the first signs of trouble when he opened his potato shed on July 24th to find condensation beading on the interior walls and a sweet, earthy smell that suggested fermentation. The plank structure, measuring 10 by 12 feet with a peaked roof, had absorbed solar radiation through its dark tar paper covering until the interior air reached 88 degrees by mid-afternoon. Overnight, temperatures dropped only to 76 degrees, trapping heat that never fully dissipated. Elias lifted the top layer of potato sacks and found several tubers showing soft spots where sprouting had begun. The crisis deepened as the heat wave extended into its second week. Daily highs remained above 90 degrees with humidity levels that made the air feel thick and oppressive even in shade. Johann's daily temperature logs revealed the growing contrast between surface conditions and his underground vault. While barnyard air peaked at 99 degrees on July 28th, The stone chamber maintained its steady 51-degree reading with variations of no more than 2 degrees over 24 hours. Conventional storage buildings across the valley began failing in measurable ways. Samuel Owens opened his shed to discover that interior temperatures had reached 94 degrees, creating an environment where his stored potatoes were essentially cooking in their own moisture. The biological processes that normally proceeded slowly at proper storage temperatures accelerated dramatically in the heat. Potatoes held above 70 degrees for extended periods began converting starches to sugars, developing the sweet taste that indicated cellular breakdown. Those approaching 80 degrees sprouted visible green shoots as dormancy ended and growth resumed. The mathematics of spoilage became brutally clear as neighbors tallied their losses. Modern agricultural science would later establish that each 10-degree increase in storage temperature roughly doubles the rate of deterioration in root vegetables. Johann's vault, holding steady at 51 degrees, provided ideal conditions where cellular respiration proceeded slowly and sprouting remained dormant. His neighbors' sheds, running 20 to 30 degrees hotter, created environments where spoilage accelerated exponentially. Mr. Carter arrived at Johann's farm on August 2nd carrying a borrowed thermometer and a skeptical expression. He had been fielding complaints from customers about failed storage systems and wanted to verify the temperature claims that were beginning to circulate. Johann led him down the stone steps into the vault where Carter could read both thermometers simultaneously, his own instrument and Johann's permanently mounted gauge. The readings matched within a degree, 52 degrees in the vault, 96 degrees in the blazing afternoon sun above. The merchant examined the storage racks where Johann's potatoes sat in neat rows, their skins dry and firm to the touch. No condensation beaded on the tubers themselves, though moisture collected on the limestone walls near the entrance, where slightly warmer air met the cool stone. The vegetables showed no signs of sprouting, soft spots, or the sweet fermentation smell that plagued surface storage. Carter lifted several potatoes, noting their weight and firmness, before ascending back into the punishing heat above ground. Word of the vault's performance spread through the farming community as neighbors compared their mounting losses. Elias Brandt calculated that 37 of his 80 stored bushels showed signs of deterioration serious enough to threaten winter food security. Another neighbor, working a smaller operation, lost nearly half of his 40-bushel potato harvest to heat-induced spoilage. The financial implications extended beyond immediate food loss. Families facing shortages would need to purchase replacement stores at winter prices that could run 50% higher than harvest time costs. Johann's wife, Anna, began keeping detailed records of their vault's contents, noting not just temperatures but the condition of specific vegetable varieties stored at different locations within the chamber. Potatoes stored near the back wall, farthest from the entrance, showed virtually no deterioration. Root vegetables on the upper racks, closer to the vault's crown, remained as firm and fresh as those at floor level. The stone structure's thermal mass absorbed and dissipated the small amounts of heat generated by vegetable respiration, maintaining uniform conditions throughout the storage space. The turning point came during the heat wave's third week when desperate neighbors began approaching Johann about temporary storage arrangements. Elias arrived with his remaining sound potatoes, perhaps 40 bushels salvaged from his original 80, asking if the vault could accommodate emergency storage. Johann agreed, establishing ground rules to maintain proper air circulation and prevent overcrowding that could trap moisture and create localized warm spots. Over 2 evening sessions, they relocated salvageable stores from failing sheds into the cooler environment of the stone vault. Even with the additional load, interior temperatures rose only 1 degree, stabilizing at 53 degrees as the limestone walls and surrounding earth absorbed the extra heat generated by increased vegetable mass. The rescue operation demonstrated the vault's capacity to buffer thermal loads that would overwhelm surface storage buildings. By August's end, the temperature differential between Johann's vault and conventional storage had created a stark division in the farming community's food security. His underground chamber had preserved 97 of 100 stored bushels with minimal loss, while neighbors using above-ground methods faced shortages that would affect their families through the coming winter. The numbers told a story that no amount of conventional wisdom could refute. The man they had called a fool had built the only structure in the valley that could maintain proper storage conditions when the weather turned brutal. The stone vault became a refuge that transformed Johann's position from village eccentric to community lifeline. By early August, 3 neighboring families had moved portions of their salvageable stores into the cool chamber, creating an informal cooperative that none of them had anticipated. Johann established careful protocols for the shared storage, insisting that each family's sacks remain separated by wooden dividers and that no containers touch the limestone walls directly. Air circulation patterns that he had observed during the vault's first season guided his placement decisions, keeping the heaviest loads toward the back where temperatures ran most consistent and ensuring that pathways remained clear for the gentle airflow that prevented moisture buildup. Samuel Owens arrived with 28 bushels of potatoes that represented his family's entire surviving winter stores, having lost more than half his original harvest to the relentless heat. He watched Johann demonstrate the spacing requirements, noting how 6 inches of clearance between sacks and walls allowed cool air to circulate around each container. The thermal principles were becoming visible even to untrained eyes. The vault's thick stone absorbed heat slowly during the day and released it gradually into the surrounding earth, while thin plank walls in surface sheds conducted heat rapidly from blazing exterior surfaces directly to the stored food inside. The engineering behind the vault's success revealed itself through daily temperature measurements that Johann recorded with methodical precision. Surface air temperatures continued to spike above 95 degrees, but the readings 8 feet underground remained locked between 50 and 53 degrees regardless of conditions above. The limestone walls, measuring 2 feet thick at their base, provided thermal mass that buffered temperature swings through their sheer weight and heat capacity. Even more critical was the vault's connection to the Earth's stable temperature zone, that layer of soil below the frost line where ground temperatures hovered near 50 degrees year-round, unaffected by seasonal weather patterns. Elias Brandt brought his engineering concerns to Johann during one of the evening storage sessions, worried that the additional weight of rescued vegetables might compromise the barrel vault roof structure. Johann led him through the load calculations that his grandfather Friedrich had taught him decades earlier. The arch design distributed weight along its curved surface, channeling downward forces into the massive side walls where they dispersed harmlessly into the surrounding earth. The 4 feet of compacted soil above the crown added roughly 80,000 pounds of static load, but this overburden actually strengthened the arch by keeping the limestone voussoir locked in compression, the loading condition where stone performed best. The vault's ventilation system demonstrated subtle sophistication that became apparent only under the stress of increased storage demands. Johann had installed 2 clay pipes during construction, one drawing cool air from near the floor level, another allowing warmer air to exit near the crown. This thermosiphon effect created gentle circulation that prevented the buildup of carbon dioxide and ethylene gases naturally emitted by stored vegetables. Without mechanical fans or external power, the system relied entirely on density differences between cool, dense air and the slightly warmer, less dense air that rose toward the exit pipe. Community dynamics shifted as the vault's capabilities became undeniable. Mr. Carter, who had previously dismissed the structure as wasteful overbuilding, began asking technical questions about construction methods and material costs. His general store served customers throughout the valley, many of whom were now dealing with food storage crises that his recommended solutions, improved ventilation, chemical treatments, and standardized shed designs had failed to prevent. The merchant's authority as a source of modern agricultural advice was being quietly undermined by a farmer who had trusted traditional methods over printed recommendations. Anna Keller maintained detailed inventories that revealed the vault's capacity to preserve not just quantity, but quality of stored food. Potatoes that had spent weeks in the controlled environment showed no signs of the sugar conversion that occurred in heat-stressed tubers. Their flesh remained firm and white when cut, without the sweet taste that indicated cellular breakdown. Root vegetables maintained their crisp texture and bright colors, while those rescued from failing sheds often showed the woody, fibrous consistency that developed when storage conditions exceeded biological tolerance ranges. The social implications of successful food preservation extended beyond individual family security to community stability during what locals were already calling the worst summer heat in memory. A family of 6 typically consumed 1 to 1.5 bushels of potatoes weekly through winter months, meaning that losses of 40 or 50 bushels represented 6 to 8 weeks of missing calories during the lean period before spring gardens began producing. Johann's vault had prevented this shortage not just for his own household, but for 3 neighboring families whose children might otherwise have faced genuine hunger by February or March. The rescue operations required careful planning to maximize storage efficiency within the vault's fixed capacity. Johann experimented with stacking patterns that utilized vertical space without restricting airflow, settling on a system where potato sacks were limited to 2 layers against the back wall with wooden spacers maintaining air gaps between levels. Root vegetables like carrots and beets, which generated less heat than potatoes, could be stored in tighter configurations near the entrance where slightly higher temperatures would not trigger spoilage. Financial calculations began emerging as neighbors tallied both their losses and the value of food preserved through vault storage. Potatoes purchased in winter markets typically cost 50 to 75% more than harvest prices, meaning that each saved bushel represented significant economic value beyond its nutritional importance. Samuel Owens estimated that vault storage had preserved nearly $40 worth of food for his family, more than twice what Johann's entire construction project had cost per household if the expenses were shared among the cooperative's members. The vault's performance during the crisis established Johann's methods as practical solutions rather than eccentric experiments. Neighbors who had once mocked his deep excavation and massive stone walls now requested detailed explanations of drainage systems, mortar recipes, and arch construction techniques. The man they had called foolish for digging too deep had created the only storage system in the valley that could maintain proper conditions when conventional wisdom met extreme weather and failed completely. The final accounting came in early September, when the heat wave finally broke and neighbors could assess the full extent of their losses without the urgency of ongoing crisis. Johann spread his temperature logs across the kitchen table, creating a detailed record that would become the mathematical foundation for understanding why his vault had succeeded where conventional methods failed. The numbers told a story more compelling than any theoretical argument: 42 consecutive days where outside temperatures exceeded 80 degrees, with 23 days above 90 degrees. Yet the vault's interior had never risen above 54 degrees or fallen below 49 degrees. Elias Brandt arrived with his own careful tallies. Having spent 2 days sorting through his remaining stores and calculating losses, with the precision of a man whose family's winter survival depended on accurate numbers. Of his original 80 bushels of potatoes, 43 remained in condition suitable for long-term storage. The rest showed varying degrees of heat damage, some sprouted beyond recovery, others soft with the beginning stages of rot that would spread rapidly once temperatures dropped and moisture increased. His financial loss exceeded $35 at current market prices, but the real cost would come in winter when replacement food commanded premium rates. The contrast with Johann's preservation results created a stark demonstration of thermal management principles that few farmers had previously understood. His vault storage had lost fewer than 3 bushels from the original 100, and those losses came from mechanical damage during handling rather than heat-induced spoilage. The salvaged vegetables from neighboring farms had fared nearly as well. 32 of the 35 bushels rescued from failing sheds remained in excellent condition after weeks in the controlled environment. Samuel Owens requested a detailed explanation of the temperature differentials that had created such dramatically different outcomes. Johann led him through the measurements with systematic precision, showing how surface air temperatures had peaked at 99 degrees while the vault maintained 52 degrees, a 47-degree difference that represented the margin between successful preservation and catastrophic loss. More significantly, the vault's daily temperature variation never exceeded 4 degrees, while surface conditions swung through ranges of 20 to 30 degrees between dawn and mid-afternoon. The biological mechanisms behind these temperature effects became clearer as Johann explained what his grandfather Friedrich had taught him about cellular respiration in stored vegetables. Root crops maintained in proper conditions. Temperatures between 45 and 55 degrees with controlled humidity remain dormant, consuming their stored energy slowly and resisting the sprouting that marked the beginning of deterioration. Heat-stressed vegetables accelerated their metabolic processes, converting starches to sugars, breaking down cellular structures, and creating conditions favorable for bacterial and fungal growth. Mr. Carter returned with questions that revealed his growing understanding of the vault's engineering principles. He had been researching storage methods in agricultural publications, looking for explanations of the temperature control that his recommended shed designs had failed to provide. The merchant's inquiries focused on the relationship between thermal mass and temperature stability, why thick stone walls surrounded by earth could maintain steady conditions while thin plank construction fluctuated wildly with ambient air temperatures. Johann demonstrated the concept by leading Carter through a comparison of heat conduction rates in different building materials. Wood conducted heat roughly 4 times faster than limestone, meaning that temperature changes at the exterior surface of a plank wall transmitted rapidly to the interior space. The vault's 2-foot-thick limestone walls slowed heat transfer dramatically, while the surrounding earth provided an enormous thermal reservoir that absorbed excess heat during the day and released it gradually at night, preventing the temperature spikes that destroyed stored food. The vault's connection to stable ground temperatures provided the fundamental advantage that no surface structure could replicate. 8 feet below grade, Pennsylvania soil maintained temperatures within a few degrees of 50 year-round, unaffected by seasonal weather patterns or daily temperature swings. Johann's design had essentially tapped into this natural cooling system, using the Earth's thermal mass to buffer his storage space against surface heat waves that overwhelmed conventional buildings. Community interest in vault construction methods intensified as the practical benefits became undeniable. Samuel Owens spent an afternoon studying the limestone arch, asking detailed questions about voussoir cutting, keystone installation, and the wooden centering system that had supported the structure during construction. He traced the load paths that channeled weight from the arch crown through the curved stonework and into the massive foundation walls, beginning to understand how the design distributed forces that would crush a flat roof under similar loading. The economic implications of successful food preservation extended beyond immediate household savings to broader community resilience during difficult years. Johann's detailed record showed that vault storage had preserved nearly 200 bushels of food that would otherwise have been lost to heat damage, enough calories to sustain several families through months when purchased replacements would strain household budgets severely. The collective value of this preserved food exceeded $300 at winter market prices, representing wealth that remained within the farming community rather than flowing to distant suppliers. Anna Keller began documenting the vault's performance in letters to relatives in other Pennsylvania counties, describing both the construction methods and the preservation results with the thoroughness of someone who understood that practical knowledge needed careful transmission to future generations. Her correspondence included temperature measurements, storage capacity figures, and construction cost estimates that would allow others to evaluate whether similar projects made economic sense for their situations. The transformation in community attitudes toward Johann's methods crystallized during a late September gathering when neighbors requested formal instruction in vault construction techniques. Men who had mocked his deep excavation and massive stone walls now asked for detailed measurements, material specifications, and construction schedules that would allow them to build similar structures before the next growing season. The crisis had converted skeptics into students, proving that practical results carried more weight than conventional wisdom when family food security hung in the balance. The vault's success established new standards for food storage throughout the valley, demonstrating that traditional methods adapted to local conditions could outperform modern solutions based on standardized designs and mass-produced materials. Johann's investment in thick stone, deep excavation, and patient construction had created infrastructure that would serve multiple generations, while his neighbors' quick plank sheds had failed their first serious test against extreme weather. Spring construction began in earnest as Samuel Owens and Elias Brandt commenced their own vault projects, following Johann's detailed specifications while adapting the design to their specific sites and resources. Samuel selected a natural slope behind his barn where drainage would flow away from the excavation, while Elias chose higher ground near his existing root cellar that could be expanded into a larger stone chamber. Both men committed to the full 8-week construction timeline that Johann insisted was necessary for proper stone setting and mortar curing, rejecting the shortcuts that might compromise long-term structural integrity. The teaching process revealed the depth of traditional knowledge that Johann had inherited from his grandfather's Germanic building methods. Each step required specific techniques that industrial construction manuals rarely addressed: selecting limestone with consistent grain patterns, mixing lime mortar to proper consistency, and shaping voussoirs with the precise angles needed for stable arch construction. Johann spent days demonstrating chisel work that created tight joints between arch stones, showing how each voussoir had to be cut individually to match its position in the curved structure. Samuel's vault took shape as a smaller version of the original design, measuring 8 by 10 feet with a 6-foot interior height suitable for his family's storage needs. The reduced dimensions allowed him to complete the excavation in 2 weeks rather than 3, but the stonework demanded the same meticulous attention to level courses and proper mortar joints that Johann's larger structure required. The arch construction proved most challenging, requiring wooden centering that Samuel built from oak lumber under Johann's guidance, creating the precise curve that would support limestone voussoir during the critical curing period. Elias opted for a 10 by 12-foot chamber that would accommodate his larger farming operation, though he chose to reduce the wall thickness from 2 feet to 18 inches to minimize stone hauling and mortar work. Johann cautioned that thinner walls would provide less thermal mass and potentially higher interior temperatures, but agreed that the modification would still deliver substantial improvements over surface storage while reducing construction costs by roughly 20%. The lime mortar preparation became a community learning experience as neighbors discovered the chemistry behind durable stone construction. Unlike quick-setting Portland cement that was becoming available through building supply companies, traditional lime mortar required weeks of slaking and aging to develop proper working characteristics. Johann demonstrated the mixing process that combined quicklime, sand, and water in proportions that created mortar strong enough for load-bearing walls, yet flexible enough to accommodate the slight movements that occurred as structures settled into their foundations. Construction techniques spread through informal networks as farmers shared labor and expertise during the intensive building period. Men skilled in carpentry contributed to centering construction, while those experienced in stonework helped with foundation laying and arch assembly. The collaborative approach reduced individual labor costs while ensuring that multiple families acquired the technical knowledge needed for future vault maintenance and expansion. The first season's performance validated the expanded construction program as the new vaults demonstrated temperature control comparable to Johann's original design. Samuel's smaller chamber maintained steady temperatures between 48 and 52 degrees through the summer, while Elias's thinner-walled version ran slightly warmer at 53 to 56 degrees, but still provided dramatic improvements over surface storage. Both structures preserved their contents with minimal losses during a moderately hot summer that would have caused significant spoilage in conventional sheds. Word of the valley's storage success reached surrounding counties through market connections and family correspondence, generating inquiries from farmers who had experienced their own heat-related losses during recent difficult seasons. Anna Keller's letters to relatives in Lancaster and Chester counties included detailed construction drawings and material lists that allowed distant families to evaluate vault construction for their situations. The documentation process transformed local innovation into transferable knowledge that could benefit Pennsylvania German communities throughout the region. Mr. Carter's general store began stocking lime mortar ingredients and specialized stoneworking tools as demand increased for vault construction supplies. The merchant's initial skepticism evolved into practical business opportunities as he recognized the economic advantages of storage systems that prevented food losses during extreme weather. His product recommendations shifted from promoting quick shed construction toward supporting the more capital-intensive but ultimately more reliable underground storage methods. The long-term implications of successful vault adoption became apparent as families planned expanded food production based on reliable preservation capabilities. Farmers who had previously limited root crop plantings to immediate consumption needs began increasing acreage devoted to potatoes, carrots, and turnips. knowing that proper storage would allow them to market surplus crops during winter months, when prices typically rose by 50 to 75% above harvest time levels. Structural durability emerged as another advantage of stone vault construction, as the original chambers required minimal maintenance through their first decade of use. Johann's limestone walls showed no signs of deterioration or settlement, while the barrel vault roof maintained its structural integrity despite annual cycles of freezing and thawing that affected the surrounding soil. The lime mortar joints remained sound, demonstrating the longevity advantages of traditional materials over newer, industrial products that promised faster construction at the expense of long-term performance. The educational legacy expanded as Johann began formally documenting construction procedures in written form, creating detailed specifications that could guide future builders without requiring direct instruction. His manual included material quantities, tool requirements, and step-by-step procedures for excavation, stonework, and finishing that preserved the traditional knowledge for transmission to subsequent generations. The documentation process reflected growing recognition that practical building methods developed through centuries of trial and refinement deserve preservation alongside newer industrial techniques. Community food security improved measurably as multiple families gained access to reliable storage systems that could maintain proper conditions regardless of weather extremes. The collective storage capacity created through vault construction provided resilience against crop failures, market disruptions, and transportation problems that could threaten food supplies during winter months. Johann's initial experiment in traditional building methods had evolved into a network of preservation infrastructure that strengthened the entire farming community's ability to withstand agricultural uncertainties. The vault network represented successful adaptation of Old World knowledge to American conditions, proving that immigrant traditions could provide practical solutions to frontier challenges when properly applied and systematically implemented. Johann's willingness to invest time and resources in proven methods rather than accepting expedient shortcuts had created a model for community development based on durable infrastructure rather than temporary fixes.